Swayam Prabha. Digital India. Educated India.
Welcome to this edition of Advanced Reaction Engineering. We will look at what we will do in this course over the period of the next 40 lectures or so. So, quickly try to tell you what we plan to do for you. In the last edition of course overview, we looked at some of the features that we might do. So, we go on with that. So, we look at energy balance, and we mentioned in the last edition that energy balance, we look at two issues. One is stirred tanks and tubular vessels. Now, we also mentioned that stirred tanks are quite popular, particularly in small scale processing, and while tubular vessels are generally very large scale processing. Now, whether it is small or large, we need to be able to conduct the chemical reactions of our interest, and therefore, adding and removing of heat and controlling the temperature at which we will conduct the reaction is crucial to success of the operations that you and I will do. So, we have to write the energy balance and understand how the energy heat is generated in the reaction and so on. Therefore, balances that we write take into account all these features, which we will do. Okay. Now, a related issue that all of us recognize is that when you are running a process, clearly there is something called startup, there is something called shutdown, there is something called safety and sudden issues, as a result of which you may have to shut down processes and all, or transient operations become crucial. Okay. Now, transient operations are issues in which we have to understand how the process deals with various kinds of disturbances that might happen in the process. In other words, when there is a disturbance to a process, we must know whether that disturbance will cause irreversible damage to the process, or the disturbance is such that the process is able to adjust itself and return to its original state. In other words, we need to understand what is called a stability of, we call steady states. Okay. So, we will look at some of these issues as we go along. In other words, what we are trying to say is that what is most important to us is that our process should be safe, number one. Two, that if there is a disturbance, it must return to its original state in reasonable period of time. Okay. And therefore, the design must take into account whether this is able to do that, or in other words, what is it that we must do in design so that it happens the way we want it to happen. Okay. So, this is what we mean by stability, and we will look at some of these issues as we go along. Now, a related, perhaps no less important, is we must look at we must know how to apply the equation that we have derived for various situations, and therefore, we look at practice problems, great variety of practice problems, okay, wherein we formulate our problems in such a way that we are able to come as close to reality as possible, or in other words, we look at situations which are as close to reality that we might encounter. Okay. Or not. So, what we are saying is that all practice problems that we will do in this course will be something that we might be able to make use of in daily life. Okay. That is the kind of selection that we have done. Okay. Now, there are few things that we must draw our attention. Let us say we have a chemical reactor. Okay. let us say we have this chemical reactor is heated, this is cooling or heating, let us say cooling. Typically it is cooling or it can be heating as well, this is the reactor. Okay. Now, frequently our intention, our interest is to be able to operate this at constant temperature, constant T. Okay. Now, if this is an exothermic, say its reaction goes A goes to B, let us say it is exothermic. Okay. Therefore, heat of reaction, heat is evolved. Okay. But and there might be a catalyst. Okay. Let us say this it's got a catalyst, inside here is a catalyst, okay, which might undergo some deleterious processes may take place as a result of which catalyst may lose its activity and so on. So, our interest would be to operate this at a temperature which is most suitable for this catalyst, let us say some temperature which is most suitable for this catalyst. Now, the question that is of interest to us is that is it really possible for a reactor to be operated at a constant temperature, while we have to deal with a reaction which is exothermic, a reaction which has got a catalyst, a reaction in which a catalyst is undergoing some kind of deactivation or poisoning, whatever, because of the reaction. Now, the answer to this is that yes, it is possible. There is a design that you and I must do, so that this becomes possible. Or in other words, we must have a design. We must have a design. If this is the distance along the reactor, okay, and if this is temperature, we want this to be just the same, irrespective of what happens in the reactor. And that is the design. In fact, as we go along, we will set up our equations and then ask this question to all of us, and what is it that we must do to see that the temperature does not change. Okay. In other words, in formulated in the language of chemical reaction engineering, what is it that we must do if this is volume which changes, or distance or volume, what is it that we must do this does not change along the length of the equipment. Okay. So, these are very interesting situations, and we will look at them and we will formulate equations and then come to a stage wherein we can tell exactly how we can achieve constancy, which otherwise seem not very easy inside such kind of tubular vessels. So, these are all what we call as practice problems, in the sense where we learn to use the equations that we have derived to be able to describe our requirements or to achieve the requirements of our process. Now, there could be situations, let us say for example, there could be situations, I mean all of us know that, see, we burn coal combustion, okay. We burn coal combustion to generate steam, and then this is then drives a turbine, and then it gives us electricity. This is something that we all know. Okay. Okay. In other words, what we generally do in the industry is that we burn coal in a boiler, and then there is water, high pressure water going through the pipes or tubes in the boiler. So, in other words, it is an indirect contact. Contact is not direct, but indirect. Okay. Or in other words, the energy or heat of combustion is directed into steam. That is how we derive energy. Now, we will, as we go along, we will consider situations. We will consider situations where we have a chemical reaction. Let us say A goes to B, okay, and then B goes. There is a chemical reaction. Can we conduct this chemical reaction in, for example, in a turbine, so that we derive energy or power directly out of chemical reaction? Or in other words, can we, we are used to conducting chemical reactions in a boiler and making steam and then using that steam in the generator and so on, but we can also look at situations where we can actually conduct the reactions in this turbine itself, so that we derive energy directly. Is this possible? If so, what does it mean? What are the numbers that would be appropriate? What are the systems that we might look at, and things like that. In other words, chemical reaction as working fluid in a turbine. as an example, can we do this? We would like to, I am now like to pose this question and see whether there are situations where we can look at, which might give us this kind of flexibility in deriving energy from a chemical reaction in the form of electricity and so on. Okay. So, I mean what I am trying to put across to you is that these practice problems are problems that try to present a way of looking at the equations that we derive in a form that we can use them in daily life for our applications. For example, it is common in process industry that let us say there are reactions, A goes to B and then, but A also goes to C, and this might be a desired product, okay, and this might be an undesired product, correct. So, in other words, our concern, our interest in design is to see that we maximize the desired product and minimize the undesired product. So, there would be design or criteria that we can derive based on the equations of material energy balance that will tell you how to find the conditions of optimality, so that we can drive your process in the direction of our interest. So, we will look at such practice problems as well. No, there are situations, for example, where a reaction is very rapid, instantaneous. Okay. So, when a reaction is instantaneous, or in other words the rate processes are so large that we cannot write equations which involve very large quantities. So, there will be methods that we must derive from our basic principles that will deal with instantaneous reactions, where heat energy is involved, heat energy exchanges are involved. So, we will look at such practice problems as well, practice problems wherein we have to deal with very fast reactions, very fast reactions. Having said this, that whatever equations that we have written for a long time is what we call as ideal reactors. By ideal reactors, what we mean is that we postulate that our reaction equipment has a certain, this is what is called as a stirred tank, continuous stirred tank reactor. This is the plug flow reactor, what we call plug flow reactor. Okay. So, what is implied here is that the time of residence of these fluid elements, okay, if all the fluid elements spend the same length of time. Okay. This is one type of device, this is an ideal reactor. Okay. And here is another instance where all the residence time here is exponentially, in the sense that as soon as material enters here, it mixes. This is what is called the well mixed or the stirred tank reactor. Okay. Now, in reality, you might not have a situation which is completely mixed, or a reality in which the residence time for every element is the same. In other words, in actuality, there could be lots of differences between, very different from these two ideal situations. Therefore, our interest of course is to be able to understand reality, okay, number one. Number two, to be able to change that reality in the direction of our interest. So, first of course, we should understand reality. So, in order to understand such reality, we will look at what is called as residence time distribution. So, the object of this kind of study is that if you have an equipment into which your fluids come and fluids go. So, what we would like to know, a fluid element that enters now, how long does it stay here before it exits? So, fluid element that enters now at t equal to 0, how long does it stay here before it exits? Now, this information itself is useful because after all we all know that the extent to which a reaction occurs is dependent on the time that it spends in the reaction environment, correct. So, what is called as residence time in the reaction equipment is something crucial to our understanding of what will happen to that reaction or our understanding of how to drive that reaction to in the direction of our interest. Okay. So, this is an important study which is able to give us insights into non-idealities. Okay. So, this is the way we try to quantify non-idealities, that is by putting a tracer and trying to see how long it stays inside the equipment. Okay. And this whole study is called as residence time distributions. Okay. So, we will look at the fundamentals of residence time distributions, and we will look at how to conduct experiments to get information on residence time distributions. We will look at how what types of tracers that we can use so that we can measure them accurately, okay, whether it is a liquid, whether it is a gas, whether it is a solid, whether it is a mixture, whatever. For different situations, there are different methods that we can use, different techniques that we can use to measure and so on. We will look at all that as we go along. Having said this, now that we understand the fundamentals of trying to do a measurement of the residence time distribution, of course, we look at practice problems. The whole object of taking this approach is that every time we develop a method, we would like to see how that method applies in real life, how that method can be used to derive insights into what happens in a process. Okay. This process can be in the chemical industry or in our daily life that you and I experience in whatever we experience in daily life. So, we would like to see that how closely can we use methods to understand what goes on around us. Okay. That is the idea of residence time. Let me just give you a small example. Residence time. Let us say, if I suppose there is a crowded railway station, and a lot of people are moving along the railway station. Now, let us say from here to here there is distance d. Now, how long does it take from going from here to here, if I ask? Okay. Now, on a day when there is no crowd, if it might take say 2 minutes. On a day when there is a lot of crowd, it might take 10 minutes. In other words, the same device, if you call this as a device, the same device, the residence time can be small or it can be large. Now, the fact that residence times change because of the load, this is the load, because of the load. So, we must be able to understand how the load affects residence time. You see, that is why we have to do such measurements, because we will be loading our equipment, and therefore, we want to know how that load affects the residence time, because that residence time will determine the extent to which our reaction occurs. Okay. So, these kinds of practice problems are crucial to getting insights into how we are able to derive information about non-idealities in a process, so that we can account for it in our design and in our operation, so that we avoid failures, troubleshooting, safeties, and all those issues arises from uncertainties in the process that we are dealing with. See, what seems to be important is that, let us say we have a gas solid reaction. Let us say you have iron oxide, let us say it is reacting with carbon monoxide, giving you carbon dioxide and iron. Okay. Now, this reaction you can conduct, let us say, in a blast furnace all over the world, okay, or it can be conducted in a smaller scale. It is what is called a sponge iron technology. Okay. Now, what I am trying to put across to you is that if there is a device, let us say it is a rotary kiln, where you have, let us say, iron oxide is coming in, and then you put your carbon monoxide, so that the reaction occurs. Just as an example, it is not the way it happens in the industry. If it is sponge iron, they put hydrogen here. If it is blast furnace, the whole device looks different. But that is not the point I am trying to get across to you. The point I am trying to put across to you is that the solids that enter the process, they may travel like this and get out, depending upon if it is a rotary kiln, we are rotating it, you see. Now, we know that it is important that we know what is the time it spends in the equipment, okay, because that depends the extent of reaction. So, if you will find that this whole RTD analysis becomes very valuable when you are dealing with solids, because solids have a residence time, and therefore, they have the extent to which the reaction will occur will depend upon how long it spends in the reaction equipment, you see. So, this is something that we know from our understanding that residence times are crucial. Of course, it is crucial for all processes, but in the case of solids we need special devices to be able to handle solids, so that the gas solid reaction can occur. Now, what is crucial, let me just put this down once again. Now, what we all know is that every reaction is governed by a certain equilibrium constant. In this case, it is this. Okay. So, the reaction stops when it reaches equilibrium, and the value of the equilibrium constant is determined by what is called, from thermodynamics we know this, that it is dependent on the partial pressure of carbon dioxide and carbon monoxide. What is important is to recognize that since the reaction stops when the value of PCO2 by P becomes Kp, it also means that as the products accumulate, the reaction starts to slow down, because the driving force for the reaction has come down, correct. So, as you go along, we will set up methods and then derive equations which will tell us how the equilibria or thermodynamics affects the rate, the rate at which the reaction occurs. Okay. That is something which is important to us, and then we use thermodynamic principles to set up equations which will tell us how the thermodynamics affects the rate of chemical reaction. Okay. We will look at that as well, some of these features. Now, when you are looking at solids, let us once again let us look at Fe2O3 giving plus CO giving you Fe plus CO2. Now, whenever we have a reaction in which solids are have to be managed, then we know that if the reaction equipment, if this, let us say if this is a reaction equipment, okay, into which we are putting solids, okay, and then let us say these solids come out. Okay. Therefore, solids going in, solids coming out. So, we need techniques to look at the particle which goes through the equipment and probably exits through the exit pipe. In other words, we need to be able to set up what is called as population balance. Why is it important? Why is population balance important? Because as a technique, this population balance is able to write balances on the number of particles. Okay. We are able to deal with number density. Okay. So, it becomes very useful when you are dealing with populations to deal with number densities. Number densities, then we can translate it to any other form depending upon what is required. But population balance is one technique by which we can deal with those kind of populations. Okay. Now, so a question that is of interest to us is that this material, let us say iron oxide, they may come with different particle sizes. Okay. The particle sizes may be distributed between two ranges. So, as this particle size of different particle size enters the equipment, of course, they will react in forms which are which is dependent on particle size. Okay. So, therefore, the inlet particles with different particle sizes will react differently and therefore, emerge differently. So, all those effects we have to account for. Population balance is a very nice technique which is available in the literature. Now, population balance we have said is useful for understanding and modeling particulate systems, but it is a technique which is which got much wider uses, and we can look at what happens in a forest, and we can understand how the birth and death functions affect the population of the forest and so on, and we will look at some of these issues as exercises as a part of this course. Now, environment is something that we all are understanding, trying to understand various issues. Now, if you look at our environment, what is it? We have the atmosphere, we have the biosphere of land, we have soil, and we have rock, and you have water, and there is carbon which is circulating between the pools as carbon dioxide, and there are other gases circulating like nitrogen in the form of protein, etc. So, all these fluxes are essentially caused by various chemical reactions by geochemical and biochemical and so on, and modeling these biochemical reactions will help us understand how the ecosystem is performing and how we can regulate our lives to see that the atmosphere and the biosphere, etc., are in good shape and good health, etc. So, these are some issues which we will look at and through certain exercises which will give us some insights into how we can understand what is happening around us. Now, having said this, I mean all of us know that ecology is what ensures that our environment is in excellent shape, and in ecology what happens is that there are many organisms, one organism living on the other and so on. Therefore, this food chain ensures that the accumulation of pollution in the environment is very small or very so small that it does not affect the population's performance, etc. Now, we would like to design systems in which we are able to integrate the ecology in such a way that our systems are able to make good use of the ecological benefits, and we will look at some problems of this nature as we go along. Having said this, so one issue of great great interest to all of us is what happens to our rivers. We know that our rivers are not in very good shape because of the great amount of pollution load that comes into the rivers, and as a result we find that the oxygen levels in the rivers are depleting, and to that extent the aquatic life which depends upon this oxygen source also tends to deplete and then lose its vitality and so on. So, of course, we need rivers, but at the same time we also need to manage the problems of populations and so on, and therefore, we have to understand how we can manage the pollution entering the rivers, so that the rivers health is kept in good shape, and these are some of the issues we would like to look at when we look at reaction engineering as applied to environmental engineering and so on. We look at some of these issues as we go along, and we all know, it is not new to us, we all know that life is governed by enzymes, and therefore, we must understand fundamentals of enzyme kinetics, and to that extent fundamentals of microbial kinetics. After all, microbial processes are also governed by enzymes in its fundamental way. Therefore, we want to look at enzymes, microbes and microbial reactions, all of which that affect our environment and so on. So, we look at some of these issues as we go along. Now, we know in our industry that we make alcohol, we make antibiotics, we make various enzymes, and alcohol is a pure culture process using Saccharomyces. Many antibiotics are produced, penicillin as an example uses penicillin, chrysogenum and so on. So, we also would like to use our principles of reaction engineering to understand how these processes can be understood, how they can be designed, how they can be operated and so on. So, some basic issues of reaction engineering is applied to these processes we will look at as exercises as we go along. Now, from the standpoint of trying to understand environment and polyculture and so on, there are several reactions that we all know that which uses polyculture. For example, waste treatment, biomethanation, and most importantly agriculture, animal husbandry, fisheries. All of these are polyculture processes where there is a food chain which is operating, and that food chain is what we must be able to understand and design for, and we will look at some of these issues as exercises as you go along. So, to cut this long story short, what is the contents of this reaction engineering course is something like this. The first 5 lectures we look at a course overview in some detail, then we look at design equations, and then we look at some illustrative examples concerned with design equations, and we go to design equations 2, where we look at wider issues concerned with design equations. Now, in lectures 6 to 8, what we have tried to do is that try to spend some time on illustrating how these design equations can be used for a variety of purposes, and several types of examples we have taken to illustrate how these equations apply. Under lecture 8, we are looking at multiple reactions. The important point is that in real life, whether it is in industry or in environment or biochemical processes and so on. We look at we deal with multiple reactions. So, some basics of multiple reactions is what we have tried to introduce in lecture number 8. Now, going on from 9 to 13, in lecture 9 what we look at is whether how to use our understanding of multiple reactions to understand reactions in soil, how these relate to various productions from soil and so on. And then we go on to in lecture 10 semi continuous operations, particularly batch, semi batch operations, where time is a critical element in the operations and so on. And 11, 12 and 13 we are looking at catalyst deactivations. I mean, catalyst deactivation, particularly in chemical process of industry, catalyst is a crucial thing, and then they are all time dependent processes. So, we have to understand some fundamentals and how these fundamentals can be used for design of deactivating catalyst processes. That is what we try to do in lecture number 11, 12 and 13. What has been said in lectures 1 to 13 is assuming that our system is at isothermal conditions, which is may not be the case always. There is an energy balance which we must consider. So, in lecture 14 and 15 we set up the basics of energy balance, and that is required to deal with stirred vessels and then plug flow vessels and so on. And 16, 17 and 18 we are looking at the applications of these basics of energy balance coupled with material balance to understand certain applications of energy balance in reacting systems. Okay. So, under 16, 17 and 18 we illustrate how our equations under energy balance can be put to use for various purposes, including design. In lecture 19, 20 and 21, essentially we are sort of taking the energy balance to greater and greater detail, trying to understand how the temperature affects rate in equilibria, how we can understand stability of stirred tanks, how we can understand illustrate this through various examples and so on. So, lecture 19 to 22 are instances where we are trying to see various ramifications of energy balance for our applications. In lecture 23, 24 and 25, 23 and 24 we are still dealing with energy balance, where of course we look at some new features, particularly heated, tubular reactors, heated and cooled and so on. So, 23 and 24 are still further extensions or further considerations of energy balance. Okay. And in 25 we do something interesting, where we try to use some measurements of operating data to see how we can design for situations where we can use some data of the process. 26 we try to introduce a new technique called residence time distribution. Of course, we have talked about it already, where we try to understand how long the fluid elements spend in the environment by using a tracer, depending upon if it's a gas or a liquid or a solid, we choose appropriate tracers and so on. So, under lecture 26 we introduce the fundamentals of residence time distributions and how they can be measured and so on. And in lecture 27 we look at models by which we can understand residence time distributions, and so that in lecture 26 and 27 we introduce the basics, so that we are in a position to model real vessels and understand the performance of real vessels. Using this basics of residence time, we go on to an important area of gas solid reactions in lecture 28, 29 and 30, where we try to understand how gas solid reactions occur. We introduce the concept of shrinking core, set up models to understand shrinking cores under different controlling regimes and so on, and then we illustrate this through examples under lecture 31. So that the idea of lecture 28, 29, 30 and 31 is to have a way by which we can understand gas solid reactions under the concepts of shrinking core models. Now, gas solid reactions we are dealing with particulates. So, when a particulate material is moving through an equipment, it has certain features of residence times and so on, we pointed out. So, when we have such variations, such interesting features in our system,
population balance modeling becomes very useful. In population balance modeling, what we try to do is that we try to understand how populations behave and set up equations which are able to describe the performance of the populations, etc. So, under population balance model lecture 32 and 33, we introduce the basic concepts, and 34 and 35 we try and illustrate how these concepts can be put to use for a variety of applications. So, basically 32, 33 and 34 we try to introduce population balance through simple examples and then try and illustrate how this can be put to use, for our applications. So, in 35 we try to move on to a new area where we try to look at reactions in our environment, whether it is for example, in soil or in the atmosphere or in the biosphere, some examples that keep this planet in good shape. I mean, what we try to say here is that reactions of the environment, whether it is photosynthesis, this respiration, there is what is called as nitrogen fixation, then there is something called biomethanation, and there is something called nitrification, denitrification, a variety of chemical reactions, mineral weathering and so on, which actually put this make this planet do what it is doing as far as life processes are concerned. So, what we try to do in lecture number 35 is to sort of overview what these reactions are and what are the basics and of chemical kinetics and thermodynamics, and how we can understand and how we can put our basic understanding of these reactions in our design of systems that we require in daily life. So, that is essentially lecture 35 is to sensitize all of us to the applications of chemical reaction engineering in dealing with environments, with our environment. With this we go on further under lecture 36, where we look at specifics of biochemical engineering and environmental engineering. For example, we try to look at what are basics of enzyme kinetics, basics of microbial kinetics, and how fundamentals of these kinetic processes can be put together in the form of design for our requirements in daily life. Having said this, we look at some illustrative examples where we take what we have learned in our basics of enzyme kinetics and microbial kinetics to understand important reactions like biomethanation, alcohol fermentation and natural selection, how natural selection happens in our environment. I mean, some simple examples to illustrate how we can understand why this great variety of things that we see in our natural environment, how we can understand them by formulating some simple mathematics to illustrate how things happen. So, lecture 37 is way of trying to apply what we have learned in the basics of microbial kinetics and enzyme kinetics to what we see in daily life. Then we go on in lecture 38 to look at some simpler things in enzyme reactions, in microbial reactions, in waste treatment, so on, trying to sort of gather more insights into the applications of the basics for understanding biological reactions. Now, having said this, one of the prime problems, particularly of water systems in India, for example, is that there is great amount of pollution that the rivers have to face because of various kinds of population pressures. Therefore, we take some examples of oxygen sag analysis of rivers, how the oxygen demand of the rivers in terms of its natural processes as well as due to interference from various pollution loads, how they can be understood and how we can regulate pollution entry into the rivers so that the river quality remains satisfactory, and what kind of design interventions can be thought of and so on in the form of mathematical formulation under lecture 39. And in lecture 40 we try to illustrate this using various kinds of miscellaneous examples. For example, under oxygen sag analysis we take some examples. Similarly, population balance modeling we take some examples, or in other words, in lecture 40 and 41 what we try to do is that try to look at miscellaneous problems that we have looked at over the entire course, and try and illustrate how what has been learned over the last number of lectures, they can be applied to understand various kinds of situations. In 42, essentially what we would like to do is a set of problem sheets which compiles a large variety of problems that can provide insights into the applications of the equations that we have derived. So, that this is all summarized in the form of problem sheets in lecture 42. In other words, what we are trying to say here is the lecture 1 to lecture 42 is trying to sort of foray into subject of chemical reaction engineering, and try to illustrate how we can use basic principles to understand how things happen around us, and how we can intervene through design to make our environment in our designs of chemical process of industry and so on, so that safety, security, productivity, economics, etc., can be achieved. Now, this whole material that we have been talking about over the last 42 lectures has been taken from various sources, and I have just listed some of these sources. One is H.S. Scott Fogler, a fantastic book written, I think it's 1986 was the first edition, and that's 2000 also is there, I think. Okay, a lot of the material that I have done in this is taken from Scott Fogler, and there is also material taken from J.M. Smith, Chemical Engineering Kinetics, a McGraw-Hill publication. Okay. And there is some material that has been taken from K.G. Denby's Chemical Reactor Theory, it's a Cambridge University Press publication, and also taken some material from Octave Levenspiegel's Chemical Reaction Engineering. It's a Wiley publication of 1997. In the sense, these books have been published even earlier. Even Fogler's book was first published in 1974. It has gone through several editions, and it's a great book which I have enjoyed. Similarly, James Smith's book, of course, it's been there for a very long time. It's a fantastic book. It's been revised and then edited a number of times. Similarly, K.G. Denby and Octave Levenspiegel, all of them are great textbooks, and material that is taken in this lecture series has been adapted from these sources. Having said this, there are a few things which we have not been able to cover, which I am hoping that we will include in course of time. That is diffusion and reaction in porous catalysts, where we look at diffusion coefficients in pores, effective factors in pores, and temperature effects in catalysts, and then catalyst design. It's a very important area. We have not had the time to look at these issues, which we will do so in future and shortly. Similarly, there is a huge area of gas liquid reactions. I mean, of industry, all of us know, and the most important application of gas liquid reaction has been carbon dioxide removal in the fertilizer industry. It's developed beautifully over the last 40-50 years. We have not had the time to look at gas solubilities in liquids, the effect of chemical reactions, and various examples to illustrate how gas liquid reaction can be understood, can be modeled, and systems can be designed for our daily use. We have not been able to do this, and hope to include this material in course of time. So, with this I thank you for your attention. Thank you.